being. You are the chairwoman.
That gave us time to grow the audience for a few extra minutes. Good morning, everybody. Welcome to the last morning of our last day.
Good morning, Julian.
Everyone.
Thanks also for being there.
So our first talk to open our last day is from Professor David Jenkins from the University of York in the UK, who is, I believe, a strong supporter of Mandela Lab and the TASTE for many years. So David, thank you for your contribution.
Thank you very much. Let me try and share my screen. Do you see the full screen?
Perfect.
Okay, great. So thank you very much, Nikita. I think it's so nice that we're all able to join together. I like this idea that this TASTE is like a linear combination of conference, summer school, and everything else. I think we should all be quite proud to be involved in this. It's really interesting that we've trying to make something good out of a very difficult year that we've had. And the whole idea of conferences and so on is changing. I think, you know, even a few years ago, we couldn't have done anything like this. The technology wasn't there. And I think while conferences have always been important in science, we always know that conferences don't work for everyone. You know, lots of people have family situations that make it hard to travel. There's other people that don't have the resources to travel, so they can be quite excluding of people. So it's really good that we've been able to construct this event, and thank you very much, Nico, for all your work on it and all your team and people like Nikita and FIFA that are chairing these sessions in putting this together. So I'm going to speak about nuclear applications, and you might be wondering why I put University of Western Cape also on the bottom here, and that's because I was very pleased to be made an extraordinary professor at the University of Western Cape last year in reflection of all the work that we're doing together. So it's very nice to have that recognize the importance of working together between countries. So nuclear applications, what I'm going to focus on today is what I would claim is how nuclear physics can make a really big impact outside of the field of nuclear physics, both in other areas of science and in the real world. And I think nuclear physics it's not unique in that, obviously, but I think in terms of these big sciences like, I don't know, astronomy and particle physics, nuclear physics tends to punch above its weight for the impact and implications it can have for other fields. So if you think of the sort of detectors which we use, let's just get the laser pointer thing, maybe a bit better. If we think about the impacts we make in other fields, a lot of the technology also is very relevant to particle physics, astronomy, and even planetary science, trying to find out what other planetary bodies are made of. But then we have very big implications into many societal areas of interest. Nuclear energy would be a very obvious one and a long established one, both in terms of detectors, nuclear data, and so on. And then the legacy of nuclear energy in terms of cleaning up former nuclear sites, so nuclear decommissioning. But there are other areas as well which are of growing importance in our modern world. Homeland security, border security, meaning people being concerned about people stealing radioactive material and moving that around or doing something with it, threatening people's safety. And then what we're going to have a particular focus on this morning with some of the other talks is medical imaging. And really a lot of this medical imaging has flown directly out of nuclear physics and the detectors that we use for that. And I mentioned another area here, borehole logging, which is where you put down detectors into the ground, down boreholes to see what minerals and so on are present. That's a nice application in that area. And I think it's very interesting that there's talks coming this morning showing how detectors are used particular to conditions and needs in different countries. So in South Africa, obviously mineral exploration, diamond mining are key industries, and we're going to hear some beautiful talks about applying this sort of detector technology in those areas as well. Okay. So I thought I'd start in a very simple place and make the simple point, really going back to high school level science, particularly for the students, that we have several types of radiation that we're interested in, the famous alpha, beta, gamma, and add to that neutrons, both fast and thermal neutrons. And the way that those different radiations interact with material is very different. So some of them are directly ionizing particles like alpha and beta particles. Some of them are indirectly ionizing particles like gamma rays and neutrons. So gamma rays, for example, scatter electrons in material, Compton scattering. Neutrons scatter off particularly protons in materials, and it's those electrons and protons that ionize and form detectors. And the consequence of the different interactions is that the alpha and beta particles interact continuously in matter, and they're stopped in a relatively short range, whereas gamma rays and neutrons, as we know, travel comparatively much further, orders of magnitude further in distance within materials. And so we have to choose detector technologies that are appropriate to those different applications. And what I'm going to do in this talk here is particularly focus on the top three, alpha, beta, and gamma, talk a bit about the detector technology and show you some interesting applications, taking detectors out of nuclear physics and solving real-world problems. I hope everyone's still with me, because all the things have gone blank. Does someone just want to wave that you're still there, Nikita?
Yes, we still see and we still hear.
Okay, I get nervous with these things because if I don't see anybody moving on a video, I start to think it's stopped. Okay. So I'm just checking.
I'll be here.
You keep your face on. That's better. Yeah.
Perfect.
I tried to watch Dean Lee's very nice talk yesterday evening, and my internet connection was terrible, and he kept sounding like a robot. So I hope we don't have the same problem today. Okay, so
very clear.
It's going fine. Good. Okay. So let's talk firstly about semiconductor-based detectors, and these are a mainstay of nuclear and particle physics, as we know. We think particularly of silicon and germanium detectors. So semiconductors have the special property of having a narrow band gap around an electron volt. And when ionizing radiation comes in, it's possible to excite electrons from the valence band to the conduction band, leaving a hole in the valence band. And applying an electric field, you can collect those electron hole pairs. And the number of electron hole pairs produced is proportional to the energy deposited in the material. And semiconductors are a special class of materials for that. Conductors would not be appropriate because the conduction and valence bands are overlapping. And then insulators, the band gap is too large, and it's not favorable to excite electrons in the same way across the gap. So let's look at applications of semiconductor detectors. And the first application I'm going to speak about is in the area of nuclear decommissioning. So in the UK where I live, the legacy of nuclear energy is particularly problematic. We were one of the first countries to have a nuclear energy. In fact, I think the first commercial nuclear reactor generating energy for the grid was built at Calder Hall in the 1950s. And there's been a lot of nuclear energy generation and so on ever since. But many of those materials produced as byproducts of nuclear energy generation, obviously very long-lived, radioactive, and nasty. And a particular one that we are concerned about in terms of how nuclear material is being processed in all these different nuclear plants is plutonium, because plutonium-239 is essentially an alpha-only emitter. and it would have been carried in liquids through pipes, and we're talking about tens of thousands of kilometers of pipes at these different nuclear installations where it could have been absorbed onto the walls of the pipes. And the pipes we're talking about are typically 2-inch diameter, roughly 50 millimeter diameter pipes. When they come to the end of the life, you're going to clean those pipes, and then you want to see whether the pipes are contaminated or not. And if they're not contaminated, obviously the pipe work can go for scrap. If it is contaminated, then you need to pay some kind of a fine and then deal with this material in an appropriate way. And the cost savings here are very, very substantial. And the fines are also very substantial if you get the judgment wrong. So if you think about it, if one of your main things you're worried about is an alpha-only emitter, then how are you going to detect it? Alpha particles, as we saw in that first slide, are stopped by a sheet of paper. So if we make a measurement outside of the pipe, we're going to see absolutely nothing. So how are we going to do it then? Are we going to section and cut up all that pipe? That's extremely labor intensive. And so we were approached to look into solutions that would allow us to make measurements sensitively of low levels of alpha contamination inside a pipe and show that the pipe work is clean in terms of contamination. So again, for the students, let's think about this problem. How are we going to detect alpha particles on the inner walls of a pipe? We might put a detector down the middle of the pipe, have it at the middle, but alpha particles lose energy even in the air. So even in centimeters of air, they can lose all their energy and stop. So if you have a detector at the center, it's not going to be very efficient. A lot of the alpha particles might get stopped already in the air. So the alternative is we could have a ring of detectors all the way around the walls of the pipe, but that's really quite complicated. We might need many individual detectors and so on. So what's going to be the best way of doing this? What struck us as the best way of doing it is to have a detector geometry which matches the geometry of the pipe. So ideally, you would like a cylindrical detector, and a cylindrical detector could be made that's as close as you can get it to the walls of the pipe so the alpha particles don't lose energy. And because it's a cylinder, and because the distance is the same all the way around, that's going to mean that the efficiency of that detector is uniform all the way around. So that's a considerable advantage. And then we got even more excited, and we haven't done anything about this, but it's interesting to think about that if you had this detector material not only formed into a cylinder, but if that material was intrinsically flexible or bendable, you could even think about a detector that changed its geometry as it went into different sections of pipe. So this is a subject for the future. So how to make a suitable detector? So our mind went to semiconductor detectors, and that's the logical choice because semiconductor detectors, like silicon detectors, are used extensively in nuclear physics and of course in particle physics in the big experiments at the Large Hadron Collider that we think about and so on. And you often see them as barrels of detectors forming an approximate cylinder, but that's not a true cylindrical geometry. It's basically planar square detectors made into a barrel. So can you actually have a true cylindrical detector? That was where we wanted to go. And well, just making the point here that this is a detector technology that we know well about, so it's a good choice of material. This is where the benefits of collaboration come in, and to my mind, I think one of the best things we can do as scientists is work with other people and talk to other people who know things that we don't. So in our department at York, we have a photonics group, and they work extensively with materials like silicon, and they have clean rooms where they can work with these materials. And they told us that if you make silicon about 50 microns thick, then like this video here, you can make it bend and conform into a cylindrical shape. Obviously, if you go too far, as at the end of the video, then it will break. But you can flex it into a curved shape. And this is a fundamental property of the material. It's crystalline, very beautiful crystal structure. It will want to just flex back into the straight version, but you can bend it and conform it and keep it to that particular shape. So that was wonderful because we saw then that we could find a material which can be bent into the shape. Its thickness is perfect because alpha particles of the energy that we want to measure are stopped by roughly 20 microns of silicon. So this is an ideal thickness. And this was our concept, our initial concept of what the detector would look like. The detector system to have a sensor around the outside of some kind of a probe or a pipeline inspection guide, as you call it. And there are similar pipeline inspection guides. I used to work many years ago with British Gas, the gas company in the UK, and they often built inspection guides, cylindrical things that go down pipes, for example, to look for cracks and faulty welding inside pipes. So this is a well-established engineering concept. The idea here is to add the sensitive detectors to it to show that you don't have alpha contamination. So these videos here, I'm not going to go into the details of this thing really, but this shows many of the processes that they followed in trying to turn these into real detectors. So there was a lot of work in the clean room facility that you buy silicon wafers, and you can see the typical wafers here. First, you oxidize the surfaces to clean them up, and then you dope them to turn them into diodes. So they were doped with ions like boron and phosphorus. So this doping was done by diffusion, meaning you put the silicon next to some material containing boron and phosphorus. Then you put it in a furnace. The furnace is here in the back for a few hours at 1,000 degrees. And those ions diffuse into the silicon and turn it into a diode suitable as a radiation detector. In fact, on commercial scale, people tend to use ion implantation. They actually accelerate ions and shoot them into the material to make it into a detector. This is more the old-fashioned technique, but in this way we can control every aspect of the process. So the guy working on this was called Christian Schuster, who's in the pictures, and if you want to read more about it, the paper published a couple of years ago is here. So here are some pictures of the detectors which were produced. So you can see the detector conformed into a bent shape over a frame. And then that was put together to build this prototype unit. So there are 4 such detectors around the ring on both ends of the detector system. We were kind of worried that this element was rather fragile, so we built a frame around it so that just these slots are where the silicon is exposed. And so there's a little indentation here, so the silicon is going to be sort of a couple of millimeters from the walls of the pipe. Here's an initial test with this plastic pipe with a americium alpha particle source mounted on the pipe. This device is pushed down the pipe, and you can see on the oscilloscope here the little pulses coming as it detects the alpha particles, and as you move it away, you see nothing. So the beauty of this sort of detector is that when there's no alpha source there, it's not really sensitive to anything else. It doesn't respond really to cosmic rays, gamma ray background in the room. In fact, we tested the detector with very large gamma sources, and you get absolutely no signal at all. So it's an extremely clean detector. And the next step of the process was to understand how quickly would you have to make these measurements to show that your pipe is clean of contamination. So we performed a Geant4 simulation, putting alpha emitters randomly on the walls of the pipe. constructed the detector element here, and then calculated how many, simulated rather, how many alpha particles you detect. And what we could show is that you want to achieve a so-called minimum detectable activity. That's the limit you want to show that the pipe is clean to in terms of alpha contamination of 0.4 becquerels per square centimeter. The becquerels are disintegration per second. And to measure that with these detectors, 4 detectors going around the ring, you could show that it would take about a few minutes per meter of pipe. So that is practical and reasonable from an industrial point of view. It means you could look at, 100 meters of pipe in a day or something. And that would be a practical sort of amount to work with. Bearing in mind, though, there are tens of thousands of kilometers of these pipes. So this is not something that might be done in a few days. We're talking about things that are done over years and years. So I have a video here, hopefully might play. I think it's, when it has a laser pointer, it won't let you select things. But. So this is more of a field trial with a real sort of pipe to give you an idea how this thing would actually work. So we were working with this company called Chromec, and this is their promotional video on the technology. You can see another version of this prototype here, more rubbery version than the earlier sort of metallic one. But you get a feeling how you would pull this thing down the pipe on a tether, inspecting as you go. And that gives perhaps a better idea how this technology would actually work. Maybe that's enough of the video. Okay, so I think that's a very nice example showing how semiconductor detectors can be taken out of nuclear physics into real-world applications. Now I want to talk briefly about scintillator detectors and how those can be used in applications. I'm going to first very briefly remind you about scintillator detectors. So there are 2 main types of scintillator materials. So scintillators produce tiny flashes of light when ionizing radiation interacts with them. We have 2 main classes. We have inorganic scintillators and organic scintillators. So inorganic scintillators are generally crystalline materials, sort of salt-like crystals, and the process which produces the light is related to the atomic structure of these materials. So electrons are excited when ionizing radiation goes through, and when these drop down back to the lowest energy state, they emit scintillation light. They emit photons in the visible or sort of ultraviolet range typically. And these are very well established technologies going back to the 1940s, 50s. The key one is sodium iodide, and people realized very early on that if you added to this pure scintillating material, which itself is not a very good scintillator, if you add inclusions of a doping of thallium, these inclusions greatly increase the light emitted and shift it into a more suitable wavelength range. So there's a whole set of these scintillators. Scintillators have undergone a revolution in recent years, in the last 10 years or decade. The main criteria people want is better and better energy resolution, and the energy resolution of these materials has been greatly increased by researching new materials, and I'll mention one of those in a moment. And these new materials are typically brighter scintillators, so they produce more scintillation light, but they're also more proportional materials, meaning that the light produced is more linearly related to the energy deposited in the material. And actually the non-proportionality can often be more important than the total light production in determining the energy resolution of these materials. But a typical number for sodium iodide, the classic material, is about a 7% energy resolution at 662 keV, which is the cesium-137 gamma ray. The other materials, and I'm going to show an example of those, so I'll talk about that briefly, are organic scintillators. So these are molecular materials made up of carbon, hydrogen, that type of thing. You can get them in crystalline form, in liquid form. They're often used for neutron detection. I'll show a specific example here, which is plastic scintillators. And plastic is obviously great because that's a material which can be molded and handled in the same way that you can any plastic which you might make cheap toys or whatever from. So in principle, you can make all sorts of shapes and sizes of this. And the process here, rather than based on the atomic structure, is based on the molecular structure of the material. So you excite the material from the ground state to the molecular excited state, but then plastics wouldn't be terribly good scintillators on that basis. And so what people do is add primary dyes to them that shifts the wavelength, makes the scintillation process more efficient, and also means that the plastics do not absorb their own scintillation light. So that's the kind of process by which they become plastic scintillator materials from a regular plastic. The main revolution, and I think that's what I want to stress here in terms of scintillators, is how we detect that scintillation light. So the main detector, the main photosensor technology, going back even into the 1940s, is the photomultiplier tube. And this is still the most extensively used photosensor for scintillators. We know the basic process, how it works. The scintillation photons fall on a photocathode. That produces electrons that are steered through this evacuated tube. We have increasing voltage between the diodes in this tube, so you get avalanches of electrons generated, and you get a large gain in signal from front to back of the tube of about 10 to the 6 is a typical gain of a photomultiplier. But in terms of industrial, medical, societal applications, this technology it's very robust, it's very well understood, but it's not terribly small. I mean, let's have a look. This is a typical photomultiplier tube. This is something going to sit in two hands. It's a large device, and maybe in some applications it's fragile because it's an evacuated tube. You also need a high voltage power supply, so you've got some electronics that go on the back of that. It's quite a big thing. That's why the development of a solid state replacement technology for this over the last decade or so has been very significant, and it's been driven actually by advances in medical imaging, particularly PET imaging, which we'll come on to in a moment. This is a silicon photomultiplier, and it's made up of each of these squares here on this device is a very dense array. So this is a sort of microscope image of it, of avalanche photodiodes. So these are little reverse biased photodiodes that when a photon falls on them, you get a big signal. They sort of flip like that. And as long as you've got more photodiodes, density of photodiodes on here, then you have photons falling on it. Typically, we're talking about tens of thousands of photons being produced from a scintillator. Then you have linearity in the signal. And these also produce a gain that's comparable to that of a photomultiplier tube. But the whole thing is the size of a postage stamp, and it's extremely thin. It can be run from low voltages like 30 to 60 volts rather than 1,000 volts. And so that means it can even be run from a battery. So this is a very interesting technology. It will not kill this technology because there are many aspects where photomultipliers can be much more suitable. But in applications work, and I think also in nuclear physics, there are many cases where this newer technology is very suitable indeed. And I'm going to show you a couple of them very briefly now. So the first is a miniaturized positron detector for assay of PET isotopes. So PET, positron-emission tomography, I'm not going to say too much about that, other than obviously there's going to be several excellent talks on that this morning about how you put a positron-emitting nucleus into a body of a patient in the form of some kind of molecule, and then this positron is emitted. It travels a short distance in the body and it annihilates to produce two essentially back-to-back annihilation gamma rays. And as we'll see in the examples today, it's not limited to applications in medicine. It's also used in industrial mineral extraction applications. We're going to hear nice talks about that. But my focus here is rather than this whole system used for the medical imaging, is how do we produce these isotopes and ascertain their purity and their radioactivity, let's say. And the standard detectors that you would buy for doing that are based on scintillators, but they're based on gamma ray detecting scintillators like sodium iodide. So you produce your positron emitting isotope and you have it in some kind of chemical form in solution. You then pass that liquid through a large lead-lined pot, and you have a large sodium iodide detector that detects the annihilation gamma rays, and you count those, and that tells you about the activity of your sample. Again, this is a very robust technology, but it's not terribly small. This is a thing like the size of a waste paper basket, and it's going to be pretty heavy because it's there's quite a bit of lead in that. So it's not a terribly small item. And we were working with colleagues in the University of Hull, which is the nearest university to us, where they do a lot more in terms of PET and chemistry and medicine. And they were interested in what are called microfluidic chips. So this is the idea of having a small plastic chip with little channels in it, and you can then manipulate these liquids. You can do all sorts of manipulations, chemical reactions, chromatography, all this type of thing, but they want to do it on a very tiny plastic chip. And that has a lot of advantages because the less material that the PET isotope is exposed to, then the purer it remains. And so everything wants to be miniaturized and made into a so-called lab on a chip. And they asked us, could you then devise a way that we can measure the activity of this sample so that we can do that part of the process too? So we said, yes, we'll try and do something on that. And this is the type of system that was constructed. So we take a plastic scintillator and we etch a channel, a very small channel into that. The liquid comes through and through this channel. So when the positrons go into this plastic scintillator, and they typically travel about a fraction of a millimeter, they produce scintillation light, and that's collected by one of these silicon photomultipliers. You can see the whole thing here. We maybe should have had a coin to show the scale, but you can see the scale here. These things are the order of millimeters. And we made direct comparisons at Hull between this new sensor that we'd made and the conventional technology, and you can see that it does the same thing. This is the number of counts you measure with a detector as plugs of this radioactive isotope are passed through the channel. So it does the same thing. And this was the PhD thesis work of Nuray, and she now is a professor in Turkey. And this is reported in this paper from a couple of years ago, if you're interested to read more. Okay, how are we doing for time? Okay, so I have another 5-10 minutes of things to show. So I'd now like to change focus and talk about gamma ray detectors for homeland security. So as I mentioned at the beginning, homeland security has become more and more important. People are worried about this idea of a so-called dirty bomb. So that means that somebody steals a strong radioactive source from a hospital or from a nuclear facility, and then they try and explode this with conventional explosive so that you would spread it around say, an urban environment. The radiation itself might not actually be very damaging to people, but I think it's obvious that the psychological damage and fear and panic that would be engendered by that would be very big. Fortunately, there's never been such an incident, but countries are very worried about this, particularly in the US. People are very worried about this idea. And so they would like to develop detectors that allow you to be continually monitoring for gamma rays in the environment, trying to see if there are radioactive sources there that shouldn't be there, even in cities or in ports. And you would like to know not only the intensity of the radiation, but you'd like to know what isotope is producing those gamma rays, identify it, and you would like to localize it. And you then think about the challenges in solving that. You know, most of the detector technology we use in our laboratories for our experiments is very bulky. It's very fragile. We couldn't easily take that into the field and start driving it around. So we need new technology to do that. And we work together with this company, Chromec, actually the same people that we worked on the alpha particle detector, to develop something, again, using this silicon photomultiplier technology shown on the top left, and coupling that with scintillator crystals, inorganic scintillator crystal. This is cesium iodide. And initially we put that together into a handheld, like a wand, a detector that you would carry around in your hand, and it would detect radiation. So you can see how compact the whole thing can be made. This thing only needs low power and low voltage, so it can be operated from a battery. So you can have a detector which can be charged up. We initially thought, when we worked on this in 2013, we thought maybe they will sell a few dozen of these and this will be quite a niche thing. But then Chromec repackaged this thing, just took the same guts of the detectors and repackaged it into a wearable or handheld unit that they called the D3S. And this has then been extremely successful. So the American government initially ordered 10,000 units of this, and it's also been ordered extensively around the world, Europe, Japan, other countries for this border security. So you can see how much of an advance that is over the more conventional technology. So that would be your classic scintillator coupled to a photomultiplier tube. It's not a hand portable device. What's not shown here is the electronics you need with it. You need a high voltage supply. This is a bulky and fragile thing, whereas this device that was developed by us in collaboration with Chromec is a handheld or wearable thing that's essentially the size of a mobile phone or pocket calculator. And so it can operate in a number of ways. It can send its information back to a phone, and it has a GPS built in. So all the time it's measuring, it knows what gamma rays it's measuring. It can identify those. It can log where you are. So it's building up a radiological map. And you also have these network versions with the idea that you can have hundreds of these in the environment in the city, let's say, worn by first responders, police and fire and ambulance, and building up a radiological map. And the beauty of this sort of device is that you can ask these people to wear it. It's not particularly heavy or complicated, and they don't need to know how to operate it. They just simply have to put the thing on and it's working. So that's a really good advance as well. And in November, it was very interesting. So this was very conventional scintillator technology. In November, Chromet launched a new version of this. And again, we did the basic research and development for them on the materials, the scintillators and the silicon photomultipliers. And this new device uses a crystal material called CLLBC. And I can't remember exactly what this stands for. Cerium. Anyway, the point is it has lithium in it, which is one of the components of this material. And lithium-6 is, if thermal neutrons fall on it, it leads to a reaction that breaks up lithium-7, producing 2 charged particles, and that produces also a big scintillator signal. So this detector is sensitive to both gamma rays and thermal neutrons by virtue of the lithium within it. And in fact, it's also a very good gamma ray detector. The energy resolution of this material is about 4% at 662 keV, and that compares to more like 6 or 7% for cesium iodide. So it's a much more sensitive detector, and it does thermal neutrons as well. Ah, somebody's drawing on my thing. That's fun. Okay, so what's happened? So I'm not really into self-publication, but I thought it's worth mentioning that a book is published last month as part of this IOP series in nuclear spectroscopy and nuclear structures. So it's actually available both as a hardback book and as an electronic book. And I think we've realized in the world we find ourselves in now that electronic resources are more and more important, much easier for students to access than libraries when we have all of these restrictions in our lives. So this book covers these case studies that I've mentioned today, and has many others as well as a major focus on the detector technologies used in experimental nuclear physics. So I encourage you to seek that out and read that for more examples of applications. And I think this is very helpful, particularly for students. You know, we're often asked to justify, why do we work on nuclear physics? Why are we doing this? You can point to these examples of how we're actually making benefits to the real world. And talking about benefits to the real world, I just wanted to talk for a few minutes about a little bit more about the work that we're doing together between ourselves at York and Nico at University of Western Cape, and Sifiso Jangase at University of Zululand, and the common projects that we have, these so-called global challenge projects. And they are in this area of nuclear applications, so it's fully fitting to this. I know Nico's shown many videos, and some of you may be getting tired of this at this stage, but let me just give you briefly my perspective on it, and maybe a little bit of background of what we've been doing together. So the UK government, like many governments, provides funding for overseas development, and overseas development can be all sorts of things tailored to individual countries' needs. Obviously, in many countries that can just be clean water supply or sanitation, the whole range of things which are relevant. But it's interesting, the program that they have, it spans all the way from that to even the high technology and cutting edge science, and working on science is equally valid within these programs. And they have this scheme called the Global Challenge Projects. And I applied with Nico and Sifiso for this back in 2017. So we had an experiment together at CERN using mini ball and Higher-Zolder, and this was fantastic because so many students came from UWC and had opportunity for training, and it was just the time when this new scheme was announced, and I thought, well, this is perfect because we could apply for this. And so we initially applied for a one-year project, which was successful. And then we moved on to a 2-year project, which is running now, that's called Mandela. Obviously, the last year has been very difficult for all of us, and it's delayed some of it, but we hope that we can extend the project and finish it well next year. And so the main focuses of this work are capacity building, meaning in this case, developing laboratories for detector development, both at UWC and University of Zululand. So I've shown you the successful examples we have of work we've done at York. We're here about sharing how to set up the capacity to get involved in this type of work, you know, to the benefit of South Africa and the wider world. And particularly, they're interested in these programs and upskilling young people. So giving new skills to people so that they're more employable, they can help support the development of the economy in different countries. So in this case, new skills in detector development, data acquisition, imaging, simulation are the things that are important. And we tied our present project to meeting needs of the country, in this case, access to healthcare and care for the environment, because we're interested in developing further the work that my colleague Dan's going to show next about quantum entangled tomography, and we see that as a possible pathway to less expensive access to positron-emission tomography. So I'm conscious of the time. I'm just going to show a few pictures, because pictures, as they say, speak more than 1,000 words. So these are pictures from the last few years of students from UWC and University of Zululand who've had the opportunity to visit us at York and learn some of these skills that we're talking about. So it's really fantastic having them visit. We already have a very international group at York. In fact, in this picture here, this is my student Aliyu, who's from Nigeria. This is Faten, she's from Saudi Arabia. And these are some of the visiting students from South Africa. And this is Pankaj Joshi, who's in charge of our detector laboratories and led a lot of the training that was provided. The other thing which we did, I think, was a very interesting experiment. So Nico mentioned before we started this morning that last year we had this fantastic meeting in Richards Bay around the University of Zululand, the Taste in Nuclear Physics. And we provided real hands-on exercises there, providing GEONT 4 training. So GEONT 4 requires a lot of computing infrastructure to set it up. And that could be a barrier to many people to get into that if universities don't necessarily have the computing support or infrastructure. And we explored doing this in the cloud. So all of the GEONT 4 was run in the cloud. We had laptops borrowed for the students, and they could then run all their things on the Amazon cloud. So we didn't need a computer system here. And these are my colleagues, Mikhail and Julien, who were providing that training, and that was very, very successful. You can see there were so many people interested that people couldn't even sit down in the room. So that's always a good sign. Again, briefly, because Nico's shown many videos of this. So the funding that I've talked about here, we helped to develop this laboratory at UWC. So this was a somewhat dilapidated space, which has been extensively renovated by UWC, and then this grants have provided new digital data acquisition and infrastructure to develop this into a laboratory where you could work on state-of-the-art detectors. And the students there called it the Mandela Laboratory, the Modern African Nuclear Detector Laboratory or something like that. But I think it's more the inspiration that's coming from let's try and get something done. And you can see the man that's leading let's try and get something done here in the middle. It's been a difficult year, but we've carried on. Obviously, the working conditions in the labs in South Africa and in the UK and elsewhere, we all have to adhere to social distancing and so on. The UWC lab couldn't really reopen until about a month ago, and so that's held back quite a lot of what we've done. Now it's reopened, we want to also spread this work to University of Zululand and develop a parallel system there so that they can work on similar things. And this was a very happy moment for Nikita, I know, and others a week or so ago, where the new digital data acquisition system was now beautifully working, and they could see nice pulse shapes and they can analyze them, and all of the interest can be done there. Okay, so I think I should come to a close. So radiation detectors are important for many applications in industry and medicine, as we know. And nuclear physics can make a unique contribution there because of the scope for innovation from the detector technology that we have. I think key things for industry that if people want to think about this more is thinking about miniaturizing things, increasing portability, making things more flexible, making them low power. These are the sort of things that are relevant and important for industrial or medical applications, and clearly it's very important. It's been, you know, one of the happiest parts of my career, I think, working with Nico and his colleagues, and the opportunity we've had to collaborate on some of the things I've shown you at the end. I think this is really going in a very successful direction, and I think we'd be very happy to have more people join in with this success. So it would be very nice to speak to people who might want to work together with us in the future. So thank you very much, Nikita.
Thank you, David. As you can see in the chat, we are all very grateful for your support. We all thank you very much. And I thank you personally. Thank you for your support and your very interesting talk this morning and the overview of all the work we've been doing at UWC going forward, also at UniZulu. You have a few questions in the chat. First, Adam, if you would like to ask your question.
Oh, yes, thank you. And thank you, Dave, for the excellent talk. I have a question, because you showed these portable detectors, which were based on this, what we were doing in the laboratory for many years. So the question is following: can you imagine that maybe some of the solutions that you can find for the portable detectors can be used back in the laboratories to improve this what we are using?
Yes. Well, first of all, let me say thank you to you, Adam, because I think by becoming involved with you on the Paris collaboration, and we worked together developing new scintillator materials and so on, that actually underpinned most of the work that I showed in that area. So I think without you, this wouldn't have happened. So thank you for that. But yes, I think one of the things we have found is it's very interesting working with industry. Obviously, industry works in different ways, on different time scales and so on. But we have found that doing some of the things that have been funded, and we've got grants in collaboration with industry, we've been able to do things that would have been difficult through more regular physics funding, let's say. And a lot of the benefits of that are coming back into physics. So, for example, we've had industry funded work to look into position sensitivity within scintillator detectors. And obviously that's very relevant for nuclear physics if you want to do gamma ray detection and localize the point of interaction in a crystal. So yes, the benefits go both ways, I think.
Thank you. We have a question from Vivek.
Vivek.
Vivek?
Yes.
Okay. I have two small questions. One is, what is the cost of the silicon photomultiplier per square centimeter, let's say, of area? I mean, have you managed to get these at a rate which is sort of, I don't know, $5 is something, $10 a square centimeter, or is it much more than that?
Yeah, the costs have been going down and down and down. So I think that the main point to say is that the main users of this technology is medical imaging and PET imaging and so on. So these people, you know, they fund the development cost and then they buy big quantities. So that helps a lot. So we recently ordered 400 silicon photomultipliers that are 6 millimeters square. And I think that these were under 30 pounds, so of the order of 30 euros or $40 or something like that, or I don't know, rupees, rands. I can't recalculate in my head, but something of this amount. So I think that means that you could tile, you know, a similar area, sensitive area to a photomultiplier tube for a similar cost. So it's comparable, yeah.
And what about the possible use of a silicon pin diode instead of the silicon photomultiplier? Of course, you have to deal with noise because you don't have gain in that. But
yeah,
is that a possibility? Because
yeah. So I think the main so he's asking about pin diodes and compared to the silicon photomultiplier. So the pin diode, the main difference is that's a simple thing, and it's a gain 1 device, whereas the silicon photomultiplier is a 10 to the 6 gain. So a silicon photomultiplier, photodiode rather, you're dominated by noise. So this is perfect if you have a big signal. If you want to detect high energy charged particles, this is ideal. But because of the noise thing, if we were doing this gamma ray detection, if we put multiple of these pin diodes, then by this so-called Groome's theorem, you think you do better by collecting more light, but because you sum the noise in series, you do no better. Whereas the silicon photomultipliers don't work the same way. So if you collect more light, then you do better. So you can benefit from tiling them. I think that's the main difference.
thank you.
May I comment? 1 minute,
Nikita? Yes.
So I would like to thank personally in front of everyone, Dave, for such a beautiful talk and your full support. Your door the doors that you open, they are opening other doors in the meantime. And for instance, Micron Semiconductor has offered training to students from UWC at this stage online, but we also have a new program to build silicon carbide detectors in our material science facility here, and we can characterize the silicon carbide detectors in Mandela. So this door that you are opening is creating, you know, it's opening more doors, and this is how things work. And this is the beauty of investing, and I really thank you for all of this. Thank you, Dave.
Thank you.
Nico?
Okay. Oh, yes, Chris.
Yeah, can I add my thanks to David also?
Of course.
As former head of assay in Solder, and also generally involved in black capacity development in the sciences, how much this interaction between you and Nico has benefited our students and of course our country also in the long term. So David, indeed, thank you very much indeed for your efforts in this regard. Yeah.
Thank you. Thank you.
Thank you, Krish. Thank you so much.
Nope. Thanks again, David. We will move on to our second talk this morning about quantum entanglement.